Imagine a high-stakes technical interview or a system design build where you are asked to traverse a graph. The pressure often triggers a specific reflex, reaching for memorized syntax. This slide introduces the formal academic concept of traversal, but in practice, many developers treat it as a script to be recited. They focus on the specific structure of a while loop rather than the physical movement of data. This reliance on memorization fails the moment the graph topology changes. When cycles or complex edge cases appear, a developer who only knows the syntax cannot adapt the logic to the new constraints. Breadth-first search, or BFS, is a geometric protocol. It is a set of mechanical rules that ensures a search expands outward evenly from a starting point. The entire process relies on the interaction of three distinct components: an adjacency list, a FIFO queue, and a global visited array. Resilient code is built by understanding these three structural mechanics. When you can visualize the interaction between the map, the engine, and the failsafe, the implementation becomes a predictable exercise in translation. BFS follows the logic of radial expansion. Starting from a single origin, the search emits a ripple that discovers every immediate neighbor before attempting to move any further into the network. This level-by-level approach ensures the algorithm maps the entire perimeter of its current position. It prevents the search from getting lost on a single deep branch before the rest of the options are even identified. A computer cannot see this geometric ripple. It is blind to the larger layout of the graph, capable only of seeing the connections tied to the specific node it is currently processing. Because the machine lacks this bird's-eye view, we must mathematically construct the expansion. We do this using specialized memory maps that force the computer to respect the radial distance from the root. To begin, the computer needs a strictly defined map of every edge in the network. An adjacency matrix is one option, but it requires the computer to check every possible pairing of nodes. In a sparse network, the machine wastes time confirming that thousands of non-existent connections don't exist. The adjacency list is optimal. It's a vertical list where each node indexed stores only direct verified neighbors. When querying a node, the list instantly identifies these connections, ignoring the rest of the network to focus strictly on relevant data. This efficiency is critical. Using a list allows the algorithm to achieve a time complexity that scales directly with the number of vertices and edges, known as O of V plus E. The adjacency list makes the map efficient, but we need a mechanical engine to force the computer to traverse that map tier by tier. If a node has 3 neighbors, the computer must delay exploring the neighbor's children until it has fully mapped all 3 initial connections. This diagram shows how we can reorganize a graph into hierarchical levels based on distance from the root. Node 1 is the root at L0. Nodes 2, 3, and 4 are tier 1. The algorithm must visit all of them before stepping into tier 2. We enforce this tier-based ordering using a queue. A queue is a rigid data structure that follows a first-in, first-out rule. When the search discovers new neighbors, it places them at the back of the line. Because the computer only processing the node at the very front, the queue physically prevents the search from jumping into deeper levels until the current level is exhausted. The queue dictates the order of exploration, but on its own, it cannot handle graphs that contain loops or cycles. Many graphs contain cycles, closed loops where nodes point back to one another. Without a failsafe, the queue will blindly re-add the same connected nodes into the line forever. The algorithm enters a catastrophic failure state, ping-ponging between the same 2 nodes in an infinite loop. To stop this, we introduce the third and final data structure, the visited array. The visited array acts as a simple Boolean checklist. It stores a value for every node index, true if it has been visited, and false if it has not. This array is initialized in a global or shared scope to track the state across the entire traversal. Before the algorithm puts a node into the queue, it checks the checklist. If the node is already marked true, the algorithm ignores it. The map, the engine, and the checklist combine to form a complete, unbreakable state machine. We can now trace the memory updates in real time. We begin by enqueuing the root, node A. In the same step, its entry in the visited array is marked true. Next is the processing phase. Node A is dequeued. The computer checks the adjacency list for A and identifies the neighboring nodes. B, and D. The filtering rule kicks in. The algorithm checks the visited array for B and D. Since they are false, they enter the queue. Nodes B and D are pushed to the back of the line, and their status flips to true, preventing reentry. This identical loop repeats. DQ, check neighbors, filter by visited status, and finally in queue, until the line is empty. By treating BFS as a rigid state machine, the algorithm explores the network without the risk of infinite loops or redundant work. This code is a literal translation of the state machine we just built. In this Java implementation, you can see the three essential components initialized at the top. The adjacency list map is represented here by the linked list array named adj. The queue engine is the queue variable, which manages the order of the nodes, and the fail-safe checklist is the Boolean array named nodes. The while.queue.empty loop is the mechanical implementation of the steps we traced. It continues the process as long as the queue contains nodes to explore. When the architecture of the graph is clear, the syntax follows as a translation of the three data structures we've identified. Understanding these mechanics allows us to define the precise performance limits of the algorithm. The time complexity is O of V plus E. Every node and every connection in the graph is processed exactly once. The space complexity is O of V. The memory used by the queue and the visited array grows in a direct, linear relationship with the number of nodes. These mechanics power critical global systems, from calculating shortest path GPS routing to finding neighbors in peer-to-peer networks like BitTorrent and indexing pages for web crawlers. This foundational logic is the starting point for nearly all advanced graph-based artificial intelligence and system design. These data structures serve as the architectural foundation for managing digital complexity across any scale.